In 10.6, we were talking about the alternating series test, and where did we leave off? I think we did that example. Yeah, so we left off talking about conditional and absolute convergence. And so this theorem here, where we say that if a series converges absolutely, then it converges. That theorem is one of the ones that follows us when we start looking at functions and representing functions as series. So when we get into chapter 11, we'll start testing those things with our absolute value, because if they converge in absolute value, then they converge. And that's what the theorem 10.19 tells us. And so the subclassifications here are infinite series are either convergent or divergent. And then even with convergent series, we can go a bit further and say, well, it either converges conditionally or absolutely. So did anyone have any questions on those? I think there were 2 examples. Is that everything all right? Okay. So the something we can do with the alternating series is put a bound on the remainder. So sometimes you'll see remainder expressed, or you might see errors. So they're kind of used interchangeably. So if we use an alternating series and say, I'm going to stop after 4 terms, we can determine how much that's actually off of the actual sum. And we're not actually going to prove the theorem itself, but it is stated below. So let's consider the alternating harmonic series and write out a few terms here, just to kind of see where some of this stuff in that theorem comes from. Okay, so first 6 terms. The sum of the alternating series is typically expressed as natural log of 2, alternating harmonic rather. We did see that was a conditionally convergent series, so in actuality it could sum to anything we wanted it to sum to. But let's just say for what we're doing here that it sums to the natural log of 2, which is traditionally what people say it sums to. And then look at, let's say, the first 4 terms. So if we use the first 4 terms, this would be our 4th partial sum. And we'll call the actual value of the series just capital S for sum. What we'll call the rest of the stuff that we didn't consider, that's still contributing to the sum, we'll call that our remainder. So R sub 4, the remainder, when we use 4 terms to sum that series. So the 4th partial sum plus the remainder is equal to the sum. And we're just using this as a specific example, but we can rearrange this and say that the sum minus the actual sum minus the 4th partial sum is the remainder, or the error in using 4 terms to describe that series. Is everyone okay with that? Then we sort of make that general, but hopefully that's pretty straightforward. In general, R sub n, the remainder or the error that we get for using n terms to sum that series, is the sum minus the nth partial sum. And then since it's alternating, we'll just look at the magnitude. So we'll be able to say like the error is at most, you know, whatever, 0.5, or the error is at most 0.2, etc. And then we can look at a figure for this, but the actual sum minus the nth partial sum is less than the next partial sum, n plus 1 minus the nth partial sum in magnitude. So that's if you have a non-increasing series, the sum of that non-increasing series is bound between successive terms of your sequence of partial sums. So we could verify that with any particular series that statement is actually true. However, this s sub n plus 1 minus s sub n is equivalent to what? If I took the nth plus 1 partial sum and subtracted off the nth partial sum, what would I get?
Value of n plus 1, or
There's a lot of vocab. What if I had 1 plus, just look at something really straightforward. What if that were my fourth partial sum? My third partial sum would be 1 plus 2 plus 3. If I subtract these two, what am I left with? 4, right? I'm left with 4 if I subtract these two. So s sub 4 minus s sub 3 is equal to 4, but isn't 4 the fourth term in that series? So s sub 4 minus s sub 3 equals the fourth term. S sub n plus 1 minus s sub n. That partial sum here has just one more term than the nth partial sum does. So when we subtract them, we're just left with the nth partial, the nth n plus 1th term for whatever series it's alternating or not. So I mean, and that requires a proof, a more technical proof, but that's the idea, is that the remainder in the alternating series or the error in the alternating series, using n terms instead of summing out to infinity, that error is no more than or is less than or equal to the first neglected term, right? So if we use the nth remainder, the nth error, that means in that one above, we would have this here. We would say, I'm going to use the first 4 terms, or the fourth partial sum, to determine what that is. But then the first thing that we neglected, this would be a sub 4. Our next term that we didn't consider, that's like our a sub n plus 1 here in this statement. Right, because with alternating, it's plus minus plus minus. So we know that it's not like a traditional series where we're just adding stuff together. Right? So we're saying that the error is at most, in magnitude, the size of the first neglected term. So if we have an alternating series that's convergent, non-increasing magnitude, the terms are non-increasing in magnitude, then we're able to come up with this statement here. R sub n is s minus s sub n is the remainder. Then the magnitude of the remainder or the error is less than or equal to the first neglected term, the first term of the series that we didn't use to determine an approximation. Does that make sense? So that's in other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term. So when we use an alternating series to do whatever, if we have a function that's approximated or a function that is an infinite alternating series, then we could say, well, if I use the first 5 terms of this to approximate the series, this remainder theorem or this error theorem would tell us, okay, in using the first 5 terms to approximate that series, here's how much you're off by. So the way that kind of shows up here is they give you a particular series and they say that estimate the value of a particular series so that the error is no more than 10 to the negative, or no less than 10 to the negative 3 or 10 to the negative 5. Okay. So if we're looking at this series and saying, all right, well, I'm going to sum it out to infinity, but maybe I don't want to do that. Maybe I just want to be accurate within the thousandth place or the hundredth place, right? Then we could use this theorem to say how many terms of that series do we actually have to add up so that we can have this error that's less than whatever, here 10 to the negative 3. So the magnitude of the remainder or the error is less than or equal to a sub n plus 1 So the first neglected term, or the a sub n plus 1 term here, with this alternating series would be what? So think about the alternating series test. The remainder theorem is expressed the same way, right? You've got the sum of this switch -1 to the power times a sub k. We're only looking at a sub k or a sub n. So just like when we test the alternating series, a sub n or a sub k is just the part that doesn't involve the alternating piece. Okay, so the magnitude of the error less than or equal to a sub n plus 1, we can explicitly write out what a sub n plus 1 is. It's 1 over n plus 1 to the 5th. So no matter what level of accuracy we want with this series that's given, that's always the first neglected term. And so it says the error needs to be less than 10 to the negative 3. If our error is less than this thing right here, we know our error needs to be less than 10 to the negative 3. Then that is our error, right? So our first neglected term is the error, and that error has to be less than 10 to the third, negative third. Is everyone okay with that? So then all we've got to do is take this equation here, or this inequality rather, and solve for n. So if 1 over these things are, in this relationship, then we know that n plus 1 to the 5th power has to be what in relation to 10 to the positive 3? Greater than, right? N plus 1 to the 5th has to be greater than 10 to the 3rd. Okay. Which means that n plus 1 has to be greater than the fifth root of 10 cubed, or n has to be greater than the fifth root of 10 cubed minus 1. So remember, n here just represents how many terms of that series that we're actually summing. So we calculate that value and see that n is larger than 2.98. So what is our conclusion based off of that? 3? 3 what?
Terms?
3 terms? So we'll put it all together. What about 3 terms?
Just need the sum.
We need to sum up 3 terms in that series, so the error is less than 10 to the negative 3. First 3 terms, so that the error or remainder is less than 10 to the negative 3. And so we can actually verify that. It starts at 1. So the first 3 terms in this, we would have negative 1 over 1 to the 5th. Okay. Negative 1. Second term is positive 1 over 2 to the 5th. Third term, negative 1 over 3 to the 5th. So this is our approximation. Negative 1 plus 1 over 2 to the 5th minus 1 over 3 to the 5th. Negative 0.0. Sorry, negative 0.972. 86522. Using 3 terms, that's the sum of the series. The exact value of that series, the infinite series, right, that over here is negative 0.97212. So if we compare where we're off in our approximation to the exact value of the series, it starts in the 4th place behind the decimal, right? So we're off here. But that's past 10 to the negative 3. Anyone have any questions about that? So I mean, like with series and only these types of series, it seems kind of surface level just to say, all right, well, what's the error? it's only until we start like approximating functions with these types of series where this is really, I guess, a little bit more applicable and useful. Because if you're like computing a limit or a function value or an antiderivative or a definite integral rather, using a series versus the actual function, then you can determine to what level of accuracy do I want this thing to be. Then I'll just add up 3 terms, and if it's 3 terms is not the level of accuracy that's needed, then you add up 4 terms, and if that's not it, then you would just add up 5 terms. So that's kind of how it shows up in practice. Another example involving the factorial here, again, another alternating series. Estimate the value of the convergent series so that our error or our remainder is less than 10 to the negative 3 again. Once again, the magnitude of the remainder or the error is less than or equal to the first neglected term, or is at most the first neglected term. So what is our a sub k or our a sub n for this series? A sub n would be what?
Plus 1 over 2k plus 1 factorial.
Yeah. The stuff that doesn't have the switch. Okay. And then the first neglected term that we're going to have here is the a sub n plus 1 term. So that's a sub n plus 1 as 1 over 2 times n plus 1 factorial. I'll write it like this. Or the a sub n plus 1 term is 1 over 2n plus 3 factorial. So that's our a sub n plus 1. That's the first neglected term if we stop at n, and that's as large as the remainder can be, or the error can be. So again, we know exactly what a sub n plus 1 is as 1 over 2n plus 3 factorial. And we want that error to be less than 10 to the negative 3. Or 1 over 10 cubed. Sorry, just remind ourselves again here. This is our error. And really it's the maximum error, right? So that's the maximum our error could be less than 10 to the negative 3.
Why'd you rate the 4 after the R?
Oh, I don't know. I was supposed to be an N. Okay. So it's the same thing. You've got to solve for n. If those reciprocals are related that way, we've got 2n plus 3 factorial has to be larger than 10 cubed. And so with factorials, I think it's easier to think about which factorial is actually larger than 1,000, and then we can solve for n that way. So 1 factorial is 1. We, you know, just go through this list. 6 factorial is 120. No, and then 7 factorial is what? 7 times 120, 41, 80. Is that it? 1,000.
It's 5 factorials.
Oh, 5 factorial is 120. Yeah, 5 times 4 is 20 times 6. So 6 factorial is 7. 6 factorial is 6 times 120. 6 factorial is 720. 720 times 7 is 7 factorial. So that's going to be it, whatever that is, 5,000. Is it
It's 54.
50, 40, 5,040? 5,040. So 7 factorial is the first occurrence when a factorial is larger than 1,000. So this quantity here has to be, that has to be 7 in order for 2n plus 3 to be 7 factorial. So 2n plus 3 has to be 7. So that this is true. Does that make sense? So that's when that's when n is equal to 2. So that means we have to add up n equals 2 terms so that the error in this particular series is less than 10 to the negative 3. That's kind of all we're doing in 10.6. I just want to know how many terms we have to add up. I don't think they ask for particular sums.
Add the first 2 terms.
Add the first 2 terms, right? If we want to guarantee that the error is less than 10 to the negative 3, all we have to do is add up the first 2 terms of that series. So again, we'll look at it numerically just to verify the approximation, so that our error is less than 10 to the negative 3. We would just go from 1 to 2 on that series. So the first term would be have positive 1 over 3 factorial, 1/6. Second term is negative 1 over 4 over 5 factorial. So we add up the first 2 terms to get an approximation of that infinite series to a degree less than 10 to the third. And that value here, the approximation, 0.158. 3333. The actual value of the infinite sum The actual value is 0.15 0.158529. Again, we see we're off on at the fourth decimal place with that approximation versus the actual value here. Do y'all have any questions at this point? The last couple of pages are just a summary of the tests that we've looked at up to this point. Last two pages. Yeah, that's it. All right, so that's 10.6 alternating series stuff. Final two tests in 10.7 we're looking at are the root test and the ratio test. And for these two, we're not gonna restrict it to positive terms only. These two tests will be presented in terms of absolute value, because if we know this in absolute value, if something converges in absolute value, then it converges. So these two tests are presented with absolute value. These two tests and the geometric will carry on to chapter 11 when we start determining a particular function converging to a series. These tests will follow us. So the ratio test is, we're given an infinite series, and the ratio is actually the limit as k approaches infinity, the absolute value of the k plus 1 term over the kth term. So the next term divided by the previous term. That limit at infinity is computed, and you've got three conditions. If the ratio of successive terms is less than 1, the series converges. If the ratio of successive terms is greater than 1, including infinity, then your series diverges, and the test is inconclusive if the ratio is 1. So the inconclusive part, like if that ratio, if the limit as k approaches infinity of a sub k plus 1 over a sub k is equal to 1, what would that tell us?
We don't know.
Yeah, we don't know, but why? Why don't we know? Why is that inconclusive? Right, yeah, so in order for this limit to be 1, as k approaches infinity, a sub k plus 1 and a sub k have to be the same number, right? So that doesn't tell us that things are getting smaller. It just tells us things are staying the same. The ratio test and the root test, the tail is I don't think they actually prove this in your book, but the tail of those two tests that we look at in this section are geometric. And so they behave like a geometric series. The tail, it behaves like a geometric series. So remember, if in the geometric series, if the absolute value of the common ratio was less than 1, there was convergence if it was larger than 1. So you've got a very similar thing here. I left that blank for this reason. If this is our assumption, this is sort of like the outline of the proof. But if this limit is equal to r, whatever that is, then out towards infinity we have the k plus 1 term behaving like r times the previous term. And so the sum, or the series itself rather, the absolute value of a sub k plus the absolute value of a sub k plus 1, and the next term, and so forth. At the tail anyways, behaves like a sub k. The next term is r times the previous term. So the a sub k plus 1 term is actually r times a sub k. And then again, the next term, the k plus 2 term, is r times the previous term. So we have r times absolute value of a sub k. And so forth. So if we factor out that kth term, we have 1 plus r squared plus r cubed. So that's our tail. That's geometric. That's not a formal proof, but it sort of outlines why the ratio test has those conditions. So just like with the geometric series, we went through all of that, like what if r was equal to 1, what if r was less than 1, if it's greater than 1, all that stuff. So that's kind of the idea. But the ratio test is super useful when you have factorials. Because if you think somebody gives you a series, like all the previous methods that we've looked at, like maybe computing limits at infinity on factorials is easier, I guess, in the sense of like growth rates. But we don't know how to integrate those, so like we couldn't use an integral test. They're not geometric, right? So if you see factorials in a series and it says, does this converge or diverge? Honestly, you should default to the ratio test if there's factorials present. Okay. So let's see how this works. Use the ratio test to determine if 2 over k, or 2 to the k rather, over k factorial converges. So since we have that factorial, we're going to use the ratio test, even if it didn't say use the ratio test. So our ratio r is the limit at infinity. Absolute value of a sub k plus 1 over a sub k. And that's the test regardless of the series that's given to us. In particular, this series 2 to the k over k factorial, it's always positive. So having the absolute value for this particular series is sort of redundant. I think we should start off with it because it's going to be necessary when we have things that could be positive or negative. But we have our kth term as this, and then our k plus 1 term as 2 to the k plus 1 over k plus 1, that quantity factorial. So we're going to look at the ratio of those successive terms out at infinity. The absolute value of all of that stuff. And so really in practice, this is just like the limit comparison test where it was a over b. We really looked at it as a times 1 over b. It's the same process here to simplify this. And at this point, or at the initial, oops, well, that was not enough room at all. But so like we're dealing with this. I'm gonna, to save space, I'm gonna erase this here and just multiply that by its reciprocal here. Okay, Okay, so there's a sub k plus 1 multiplied by 1 over a sub k, or the reciprocal of a sub k. See how much space I have to do with, not much. And then we want to simplify this, right, because we need to compute this limit as k approaches infinity. So the more we can simplify this, the better off we're going to be. So we've got a 2 to the k on bottom and a 2 to the k plus 1 up top. Hopefully that's pretty straightforward. I would just recommend breaking these things up. 2 to the k plus 1 is 2 to the k times 2 to the first times our k factorial over 2 to the k here. What is k plus 1 factorial? How are we going to rewrite that so that it's more conducive to us simplifying this?
K factorial times K plus 1.
Yeah, k plus 1 times k factorial. So k plus 1 quantity factorial is just k plus 1 times k factorial, right? So 4 factorial is really the same thing as 4 times 3 factorial, right? Because that's 3 factorial. Or we could even say that's 4 times 3 times 2 factorial, right? Or we could say it's 4 times 3 times 2 times 1 factorial. So every time we subtract 1 from that quantity, it's multiplied by a factorial. Does that make sense? K plus 1 factorial. This is really k plus 1 times k factorial. Okay. So that's always the trick to simplify those factorials. I mean, I get this. I guess at this point we could just keep carrying this absolute value through, but it's really redundant because they're all positive. And so this comes out our limit at infinity. We have left over the 2 to the k factorials cancel. We just have 2 over k plus 1. The limit at infinity is what? 2 over k plus 1, 0. So the ratio is 0. The ratio is less than 1. If the ratio is less than 1, your series converges. That's what we'll see. The given series converges. Anyone have any questions? Okay. So if you'll notice, a lot of these tests involve limits at infinity. And when we see that series, whatever the series is doing, a limit at infinity just determines its horizontal asymptote, right? So if we say like this series has a limit at infinity that approaches that value, It's the same thing as like our functional analysis when we said that this function has a horizontal asymptote. It doesn't quite ever, get there, but it's getting closer to it. This test is no exception. It's still a limit at infinity. So use the ratio test for this series. The kth term is k to the k over k factorial. So the k plus 1 term, k plus 1 to the power of k plus 1 all over k plus 1 factorial. So we'll just note here that the series consists of positive terms. So we don't necessarily be redundant to put the absolute value, but it's definitely worth remembering that the test does involve the absolute value. So the limit at infinity of successive terms, so the k plus 1 term divided by the kth term, or times the reciprocal of the kth term. Series consists of positive terms, so this will be more descriptive here. So we do not need absolute value in our ratio test. But even if you had like an alternating series, you could use the ratio test to test the alternating series. So you take the absolute value of the alternating part, it's just always positive. It's just that a sub k. All right, so we're going to break this up a little bit further, limit at infinity. We're going to write k plus 1 to the k plus 1 as k plus 1 to the k. Times k plus 1. Times k factorial. We're going to rewrite the k plus 1 factorial like we did in that last example. It's k plus 1 times k factorial. And this is just, we can't do anything with this, it's just k to the k. So things cancel. We've got computing the limit at infinity for k plus 1 to the k on top and k to the power of k on bottom. So what would our limit be? Infinity? What do y'all think? How do we know it's infinity? Or what's our reasoning for saying that it's infinity?
It approaches it quicker in the numerator.
And the numerator is k plus 1 to the k. The denominator is k to the k. Aren't they, for really large k, I would say that those are really comparable to one another. Like 100,001 to the 100,000th power divided by 100,000 to the 100,000. Pretty much the same thing, right? So I know it can be misleading because it says, well, this base grows is larger than k. K plus 1 is larger than k. I mean, that would be true if it were like a fixed power. Like if this were k plus 1 to the third over k to the third, then yeah, the top is going to grow a little bit faster. But it's really not exponential and it's not a power function. So you've got to look at this in a slightly different way. If you look at it that way, that's, I think, a bit misleading to look at it that way. What if we looked at it as k plus 1 over k, and it's that quantity to the kth power? Then we would say, well, yeah, the inside approaches 1, the power approaches infinity, right? So that's really like one of those far-off L'Hopital rule, right? 1 to the infinity, you've got to rewrite it. It's an indeterminate product, right? It's a pretty lengthy L'Hopital's rule process for 1 to the infinity.
Is it E?
Yeah, so like if we looked at it like k divided by k plus 1 divided by k, if we just split those two up, k divided by k is 1 plus 1 over k, like that, is the same thing as k plus 1 to the k. Or sorry, k plus 1 over k. But then if we looked at it as this, 1 plus 1 over k to the power of k, we should remember that limit. What is that limit? E. Yeah, e to any specific power, or just e?
E2.
Right. So it's, remember, this is like our a, and this is like our b. Remember that limits of those forms is, or at infinity rather, limits of those forms are e to the a times b. So this is e to the 1 times 1. So k plus 1 to the power of k and k to the k actually grow at comparable rates. They're growing at that comparable rate. But this is, all of this was for r, our common ratio. R is equal to e. Since r is equal to e and e is larger than 1, the series diverges. Okay, so if we looked at the problem from the beginning and said growth rates, what are we actually doing?
Just be the divergence.
Yeah, exactly. If we just started off the problem and said, okay, well, here's our series. What I mean, I guess when we say growth rates, we say, what's the limit as k approaches infinity on the series that's given? So this right here, that's the divergence test. So the divergence test would, by growth rates, immediately tells you that it diverges, right? We could have done that, but it said use the ratio test. So we use the ratio test.
So we'd only get partial credit.
Yeah, you're probably getting no credit. I don't know. I've tried to be lenient, like, on instructions, but especially this semester, and it's not just, it's not really in this class, it's just other classes. I specify something in the instructions and they're not followed. I don't know, it kind of annoys me. Because it's like, it's right there, it tells you what to do. So yeah, if you did that divergence test and you said the series converge or diverges by the divergence test, then you probably lose most, if not all, points for that. But all right, either way, it's not that we're saying that the divergence test is bad or we shouldn't use it. It's actually the most efficient thing in this sense, but sort of getting used to the root and ratio test. I'm gonna just add a little bit more to this here. Well, that page is getting kind of long. So like if we add just like an alternating part to that series we started with, here we would have to be careful when we compute the ratio, because we have positive and negative terms in this sequence, or this series rather. So we would look at this. I'll write what we had to begin with. Oops. So that would be our next term, our prior term. Would be this. So notice here, it does matter, like we couldn't just cancel these two things here, because one is 1 and the other one is -1, and vice versa, right? But since we do have the absolute value around that alternation, it becomes kind of a moot point, right? The absolute value eliminates that alternating part. And so from here, we're exactly where we were with the original series that didn't alternate. So we could look at it maybe one more step just to address it fully, I guess. Right, that's really all of the absolute value is there for. The other stuff with the k's here, factorials and whatnot, positive, this right here is going to be always equal to 1 because we have the absolute value. So this is equivalent to our original problem. We work through that. We see that it's E, it diverges. So it's still applicable here. The addition of the absolute value in that theorem sort of just broadens that theorem and what we can apply it to. Any questions on the ratio test? The root test, although different, we're still computing a limit at infinity, and you'll notice that these three conditions for the root they're identical to that of the ratio. So we've got two different tests, but their conclusions are exactly the same. Different process. But the root test, we're going to let rho be the limit at infinity on the kth root of the absolute value of our series, or the term rather, a sub k. Excuse me. This test again is also at the tail rather is geometric, so we've got another similar conclusion. But the kth root of the a sub k that's given. So you could, maybe envision that this would be useful for stuff that just has like the kth power attached to it, like 1 over ln of k to the power of k. We could say that our the root rho is the kth root of the absolute value of our a sub k, which is that so useful in the sense that we don't have to think about the kth power anymore because we're taking the kth root. So all we need to do is compute the limit at infinity on 1 over the natural log of k. Does that make sense? Our simplification here. Kth root of 1 is 1. Kth root of ln of k to the k is just ln of k. So that limit is equal to what? 0. In other words, our root rho is equal to 0. We have 0 less than 1. A given series converges. So at this point, we'll stop here and take a break, but if you've worked through your homework, one of the series, I think it was in 10-4, was like 4 to the k plus 6 to the k over 11 to the k. Do you remember, have y'all done that one yet? So if you're going through the help me solve this, they say, well, use the integral test, split this thing up into 2 different things and use the integral test on each thing. Like this, plus this series, whatever it is. Now we could use this, what is it, root test to take care of these kth powers here. So right, we would just take the kth power, the kth root of 4k over 11k. Much easier of a process than having to integrate that stuff. If you haven't got to that problem, then I would recommend using methods up to that point. It sort of limits yourself, right? Because it's like, well, once I know all of this, why wouldn't I just use the one that's easiest? It's totally a valid thing, but the point is to practice with these individual tests for varying types of situations. But anyways, this problem right here that was in 10-4's homework would be like a perfect candidate to use the root test on. For whatever that's worth. Probably doesn't mean anything. We'll take a break then. Okay, use the root test to determine if the following series converges. Notice this isn't just 1 minus 15 over n to the power of n. It's to the n squared. But if we utilize the root test here, hopefully that limit or that expression looks familiar. You see that when we involve the root for this particular series, the root is the limit as n approaches infinity. We're going to take the nth root of all of that stuff. And when we take the nth root of that quantity raised to the n squared power, what will that give us? Yeah, that quantity to the n, because this is 1 minus 15 over n to the n squared to the 1 over n power. So we just multiply the exponents. N squared over n is n. So we have the limit at infinity. Oops. Limit at infinity for 1 minus 15 over n to the power of n. That's that. And what is that limit? Careful. E to the negative 15. E to the negative 15. And maybe it's worth writing this limit again. We proved that in class. But that's what we're basing that off of. A is negative 15 and B is 1. So it's e to the negative 15. E to the negative 15 as the root. The root is e to the negative 15, which is less than 1. So our series converges. So rho less than 1 means that the given series converges. Okay, any questions on that? Again, it's not always, I don't think it's always straightforward, like when you're given a series, like which test would be the most efficient thing to use, which is why we have so many tests. Certain tests don't apply to certain series, and even if certain tests apply, they're not always conclusive. So we are skipping 10.8, but I think 10.8, if you just look through that, could be pretty useful, because in 10.8 it's just kind of like putting it all together. They'll say, hey, here's a series, does it converge or diverge? And then so like all of the methods from chapter 10 are applied in 10.8. And hopefully as you've seen some of these tests, it's really not, I don't think it's really the algebra or the calculus that are present in these tests that are difficult. It's one, which one do I use? And two, what does my conclusion actually tell me, right? Because all of these tests have varying conclusions. And that's really the hard part to keep straight, I think. Which test to use and what does my conclusion actually mean? Really, there's no way around it just by other than just doing it over and over. So it says use the whatever test to determine if the given series converges or diverges. What test would we use here? The ratio test, yeah. The ratio test because of the factorials that are present. Again, the terms are positive, so we can forego the absolute value here. And maybe we'll write out our terms. A sub k. Notice this is k factorial quantity cubed. And this is 3k quantity factorial. It's not 3 times k factorial. So a sub k plus 1, a sub k, k plus 1 factorial, that quantity is cubed. K plus 1 quantity factorial cubed over this k right here gets replaced by k plus 1. So we're saying that that's 3 times k plus 1, like this. But that quantity's factorial. So this whole thing factorial. So that's 3k plus 3. Factorial. So ratio of successive terms, the next term over the previous. So we have, it's kind of a mess at first. K plus 1 factorial cubed over 3k plus 3 factorial times the reciprocal of a sub k is our ratio. So in order to simplify this, like we've done with the other two, we've got to express 3k plus 3 in terms of something times the 3k factorial, so those things can cancel out, and we've got to express the k plus 1 factorial cubed as something times k factorial cubed, so those will cancel. Right? We always expect here in the ratio test that the bulk of that will cancel. So we're just going to break this up. And whenever you use the ratio test, you just want to use or kind of focus in on the kth term and express the k plus 1 term in as much as you can how the kth term looks. And that way those things will cancel out. Okay, so we want to cancel with the k factorial cubed on the bottom here. So we're going to rewrite k plus 1 factorial as k plus 1 times k factorial. And then again, since that's just k plus 1 factorial, it's still cubed, times our 3k factorial. Our 3k plus 3 factorial, we want that to cancel out with the 3k factorial. So 3k factorial, 3k plus 3 factorial. How are we gonna rewrite that?
K factorial times k plus 3k plus 3.
Okay, so 3k plus 3 is there for sure. But when we write this out, like when we subtract 1 from our factorial, like we have here, k plus 1 times k factorial, this would be 3k plus 3 times what factorial? Not plus 1. Not just k.
3k plus 2?
3k plus 2, right? So you just decrease that plus number by 1 each time. So this is 3k plus 3 times 3k plus 2. Right? Like 4 factorial is actually 4 times 3 factorial. It's just 1 less. But we want to keep going with that because we want to cancel that with the 3k quantity factorial on top. So we wouldn't stop there. We would say that's 3k plus 3 times 3k plus 2 times 3k plus 1 times 3k factorial, right? So you can keep breaking the factorials down by 1 less in that pattern for whatever that expression is in the factorial. Is everyone okay with that? I mean, it's kind of weird, but it's like if I have n plus 5 quantity factorial, I could write that as n plus 5 times n plus 4 factorial, or n plus 5 times n plus 4 times n plus 3 factorial. So just keep making it one less and scooting that factorial over. I could write it like that. Depending on what n is, I could even keep going and say times n plus 2 times n plus 1 times n minus 1 times n minus 2 times n minus 3 factorial, right? And how far you take that out is just really dependent upon what's in your kth term that you need to cancel with. Okay, so that's the 3k plus 3 factorial. We still have the k factorial cubed here. I really don't know a better way around that, because I don't think there is. And then we'll look at what cancels here. Maybe if you know, like just not to get these things mixed up here, as this first term, we could rewrite this as k plus 1 cubed times k factorial cubed is what this is here. Okay, so the k factorial cubed cancels with this k factorial cubed. The 3k factorial cancels or divides here. We've got on top then k plus 1 cubed over 3k plus 3 times 3k plus 2 times 3k plus 1. So what is that limit equal to? Yeah, it's a polynomial over a polynomial. Leading term on top is k cubed. Leading term on bottom is 3k times 3k times 3k. You could do L'Hopital's rule 3 times if you wanted, or 2 times if you wanted, but it's the idea. This limit simplifies to 1 over 27. That's our ratio. Ratio 1/27th, less than 1 means that that given series converges. Anyone have any questions? All right, so in chapter 10, we're just looking at a series and saying, does it converge? What we care about more so than anything else is what we'll see, and when we start chapter 11, is that we could take a function that has a continuous derivative, and we can express it as a series. It's you know, like a polynomial. So even though we can do that with continually differentiable functions, the question is when does that function actually equal to that polynomial? For what values of x can I deal with so that this function is this polynomial? And then that's where these tests come in, because not only will they tell us if it converges to the function, it's more specifically going to tell us for what values of x that we can plug into that function and that series so that they're exactly the same. So the idea of convergence takes on this, it takes on an equal sign. When we say this function or this series rather, converges to this function, we can say that this series is equal to this function. But we have to know for what values it converges for. And that's really where these tests help us out. So those last two examples we're gonna not do because of time. All right, so what I mean is to say, like, if I have this function arctangent, as we'll see at the beginning of chapter 11, I can say that the arctangent is approximated by this particular polynomial. But what if I wanted to say that the arctangent is this polynomial out to the 15th degree, let's say? Well, it doesn't look like it's a very good approximation to the arctangent function. But let me see if this might be a bit funky here. X. I don't know if this is actually doing that, but it should be. I'm not sure why that is doing that. So really, let me try more terms here. I don't think this will do a whole lot of terms. Maybe breaking. Okay, so we can't go out far enough. I don't think. I'm kind of curious now. I might just totally stop. Maybe not. Give it a second. Okay. So it's difficult even for this. However, we come up with this series here. Just pretend we know that inverse tangent is this series. Some of these things that we come up with and say, hey, this function is this infinite polynomial, it's not true for all values of x. In other words, you would only see that the red and the blue are, and this isn't accurate, but we would only see that the red and the blue are matching up, like in a certain interval around, maybe whatever it is. Maybe it's negative 0.2 to 0.2 where the red and the blue are the same. There, it's moving a little bit. But the idea is, when is the arctangent actually equal to that infinite series? And those tests that especially the root and the ratio and the geometric, will come in and say that this series is the same as this function, as long as we're looking at x values between whatever, 5 and -5, or 1 and -1. If we get out of that interval from -1 to +1, no longer is the arctangent approximated or equal to that polynomial. So I don't know, maybe that was a bad example because the computer, there's probably a more efficient way to program this, I just don't know. But that's kind of the whole point of all this series stuff, is to do that for us. We'll mention these last two examples though. What test should we use here? Root test, yeah. So the power of negative k, root test, we'll take that to a -1. We'll just go ahead and write this. If you're supplementing your homework, I guess. Series converges by the root test. Example 6. Example 7 is it's not in closed form, but we could certainly write out what the series is. We see the factorial on the bottom, so we're going to use the ratio test. And what would the series be? I guess we'll start at 1 and go to infinity.
K squared over
Yeah, k squared. So then we would test k squared over k factorial in the root test to see that it converges. And and actually what we're addressing here with these two tests, since the root and the ratio test have the absolute value, the conclusion would be something to the effect of, say you worked all of this stuff, okay. This thing right here, you would come up with, in this particular example, that the ratio r is equal to 0. So since the ratio is less than 1, what we really tested was the absolute for that series when we use the ratio or the root test. So really our conclusion is, first, that the series converges for all of these. So the series converges absolutely. And then, so by theorem 10.19, the series converges. Okay. So absolute convergence implies convergence. And that's going to be more important when we actually start dealing with series that have positive and negative terms. So do y'all have any questions on 10.7? So 11.1, we're going to look at power series. And the goal of power series, we're going to look at power series and then a specific type of power series. But the goal is to take something like a function like e to the x squared that does not have a known antiderivative and determine what is the area under the curve from 0 to 1. So there's many functions, you could search them, that don't have known antiderivatives. And so, you could imagine that's a problem because the fundamental theorem of calculus said that if you can find an antiderivative, then this is how you find the area under the curve or the volume or whatever. But then you run into a function where you can't find the antiderivative of, so it's like, how do you proceed? If I can't find the antiderivative, then I can't apply the fundamental theorem of calculus to determine that area. So that's where these series are coming in to help us and say, all right, well, yeah, we don't know the antiderivative of that function, but we can write that function as an infinite polynomial. Depending on the level of accuracy we want it to be, we can look at the first 5 terms, maybe we might have to look at the first 10 terms, and just integrate those powers of x instead. And a lot of that theory, I guess, is justified in chapter 10 with the work that we've done with series. So 11.1 is basically approximating functions with polynomials. And you might remember, especially from this textbook, if you took Calc 1, that the linear approximation was mentioned in 4.6. But the linear approximation to a function at some value a is just using the equation of the tangent line to approximate the function. So that's kind of what we're starting with, something that we've hopefully seen before, but then we're going to expand that to higher orders. So the linear approximation is just f of a plus f prime of a times x minus a. Sorry, it's being weird. It's okay. Or if you want to think about that, all that is the equation of the tangent line. So when it says find the linear approximation of x squared minus 5 at x equals to 1, we have our function value, or the y coordinate of that point, as 1 squared minus 5. The derivative of the function evaluated at that x value. And then we put those pieces together to find the equation of the tangent line. We say, well, the slope of the tangent line is 2. And really, it's do y'all remember the point slope formula for a line? That's really all it is. It's just a rearrangement where it's already solved for y. So we say y is y1 plus m times x minus x1. And all y1 is the function at a, the y value, right? The m in question that we're after is really the slope of the tangent line times x minus the x coordinate. x1 is a. So we just replaced the slope of the tangent line at a with f prime of a. So it's just, that's the equation of the line that we're coming up with. Okay, so we have the our linear approximation is, we'll just call it L of x for now. Linear approximation is f of a plus f prime of a, which was 2, times x minus a. So that's that. Y equals mx plus b, right? Slope, what do they call that? Point slope? No. Slope intercept, right? So what do we have? 2x, 2, minus 2, minus 4. That's our linear approximation. In other words, that's the equation of the tangent line on x squared minus 5 at x equals to 1. So just put that here. Oh, x squared minus 5. All right, so that's our function at this point. It said approximate that function at this point with a line. And so our line is negative 2x, or sorry, 2x. So, I mean, once we're zoomed out, we can see clearly that it's not a great approximation. As long as we're around that x value of 1, it's a pretty good approximation, right? We can even see we're up close, a little closer now. We can even see the difference between the parabola and the line. But as long as we're close, you don't see the difference between the line and the parabola. So if we're approximating values on that parabola near 1, we can use this line 2x minus 6 instead. And at this point, it seems kind of trivial, like why wouldn't I just plug the value into the quadratic? It's easy enough to evaluate. But what we're doing is we're taking this idea and we're extending it to higher orders so that we can approximate things that aren't polynomials. So let me just put this in our notes here. Instead of trying to draw that by hand. Alright, hopefully that's not. So since this is a linear approximation, in the grand scheme of things, we're going to call this a first order approximation. If we looked at a quadratic approximation, it'd be second order, cubics a third order, so forth, so forth. Okay. So the idea of Taylor polynomials is an extension of linear approximations to higher orders. So the nth order Taylor polynomial for f with a center at A. So when you think about, when it says center at A, that's just where the thing is, where you're constructing that polynomial. If you're given some function and it says figure out what the Taylor polynomial is centered at an x value of 2, then you're basically constructing your tangent line at 2, then you're constructing your quadratic approximation at 2. So center just means where you're constructing that approximation at, what x value you're constructing at. And so the P sub n is going to have the property that it matches f in value, slope, and all derivatives up to the nth derivative, because we're going out to the nth order approximation. The nth order Taylor polynomial centered at A is given as follows. So you'll notice that that right there is the linear approximation. And then we add another term to it. We have a quadratic, then another, then another, then another. And we'll just take that out to n, whatever n happens to be. We find the 500th order approximation if we wanted to. So there's our linear approximation hiding in it. But the pattern is the order of the derivative divided by that number factorial times x minus your center value to that power. So we see that here. The nth derivative evaluated at a over n factorial times x minus a to the nth power. So we have to keep adding that x minus a squared, x minus a cubed. Otherwise, it's not a polynomial, right? It's just, without those terms, we don't have a polynomial. And then this says more compactly, it's x minus a to the k times this c sub k. So this c sub k for Taylor polynomials is a very specific thing. When we look at power series in the next section, power series take this form but the coefficients typically are random. When we talk about Taylor polynomials, the coefficients, whatever this number is, the kth derivative at a over k factorial, whatever that number is very specific. It has to be found that way if we're talking about a Taylor polynomial. So the f prime of a over 2 factorial is just some number. That's the coefficient on the x minus a squared, so on and so forth. So think about the order as the degree of the polynomial. And so p sub 1 of x is the first order approximation of the first order polynomial, which of course we know it's just linear. You know, and so forth. If we find p sub 7, then we're finding the 7th order, or the 7th degree polynomial. Linears are polynomials too, but the 7th order polynomial approximation to or of f of x, and so forth. So like we've always done in calculus, we sort of look at the finite setting first, and then we let that number approach infinity. So that's what we're ultimately going to do with this. As of right now, these Taylor polynomials are finite. When we look at the next section, power series, that's when we're going to look at the infinite series. And then, so that's when that starts tying back into chapter 10. All right, so you really need to know how these polynomials are constructed in that sense, that this line here is the really important takeaway here. Okay, so then it says, example 2, find the Taylor polynomial of order 4 that approximates e to the x, and let a equals 0 be the center. So we need to find this p sub 4, the 4th degree polynomial. And we'll just write it out so we know what we're finding. We have f of a plus f prime of a times x minus a. Notice this thing is actually f prime of a times x minus a is actually hiding over 1 factorial, and x minus a is to the first power. Same thing with f of a. It's f of a times x minus a to the 0th power over 0 factorial. So that's hiding there as well. Plus the second derivative at a over 2 factorial times x minus a squared plus the third derivative evaluated at a over 3 factorial x minus a cubed. Does everybody see the pattern? Hopefully that's pretty straightforward. And then the 4th degree comes from the 4th derivative evaluated at a over 4 factorial times x minus a to the 4th. And of course we can simplify this a little bit because we know our a is 0. So all of these a's are 0. That's f evaluated at 0, f prime evaluated at 0. This is x squared, this is x cubed, this is x to the 4th. Okay. So really, I would start out by saying, well, I guess just find all of the derivatives necessary, perhaps is the. So we've got f of x being e to the x, and then all of its derivatives are e to the x. We want to go out to the fourth derivative. All right, so you need to find the derivatives, and then you need to, and the function, and you need to evaluate all of those at the center value, a equals 0. Move this down. Okay, whatever. I'm gonna move that down a little bit. And then we want to evaluate those at a equals to 0. And really, once we fix our variable x to say a equals 0, really what we're saying is evaluate them at x equals to 0. So as soon as we fix a value, it's a, just to differentiate from the part that's actually varying, but it's really evaluated at x equals to 0. So we have f of 0 is e to the 0, which is 1. We have f prime of 0, e to the 0 again. F double prime of 0 is also 1, and so forth. So the idea of like the higher order derivatives comes in. If we looked at that linear approximation, we can just see that they're equal in slope. Like the line itself was the exact steepness of that quadratic at that point. But then that's the first derivative comes in and does that. The second derivative comes in and then matches up concavities, right? Because the second derivative tells us the concavity. So you refine that linear approximation a little bit better by then honing in on the concavity of the function too. And then the third derivative and the fourth derivative and the fifth derivative also take care of a very similar thing. So that what we have there is the sort of the numerators of our coefficients. And then each one of these function, derivative, second derivative, third derivative, fourth derivative, those coefficients are always over the corresponding factorials. So the coefficient here is just 1. The coefficient here is 1 over 1 factorial. The coefficient is 1 over 2 factorial. This one's 1 over 3 factorial, and this is 1 over 4 factorial. So we're going to just put this all together and say that e to the x, the function e to the x is approximately the p sub 4, that fourth degree polynomial is f of a, so f of 0, which is 1, plus the derivative 1 times x minus a, x minus 0. So we'll just write this here, x minus 0 to the first. Maybe we write it like this here. That came from the first derivative. The second derivative's coefficient was also 1, so it needs to be over 2 factorial times x minus a to the second power. the next coefficient, its numerator was 1. This is from the third derivative, so it's over 3 factorial times x minus x minus 0 cubed. And then we had the next coefficient was 1 from the fourth derivative, so over 4 factorial times x minus 0 to the fourth. And so we'll clean that up a little bit. Okay, so that's the instructions wanted, is that fourth degree polynomial that approximates e to the x. And we should say that this is for x near 0. Because that was our a, that's where we constructed that polynomial about that point, or that x value of 0. So how accurate is that really? It depends. Depends on where x is at. And near is arbitrary, right? It's not specific. So how near? Don't know. So there's the quadratic approximation to e to the x near this value, right? X equals to 0. There's the linear approximation. And we have the quadratic approximation, cubic approximation. Even better. So specifically this area here, this white space here, when we add on the next term, it tightens up. And then when we add on the fourth term, it's even better. So we can see, all right, for x near 0, for when we're near this point, well, you know, maybe right around here at like, what is that, 1, 2, 3, 4, there's 5 of those. So like, you know, 1.5, we start to see that the divergence, right? There's a divergence of the series versus the function. So the series, the finite series, is no longer converging on that function. It's a little bit better out this way. We start to see that difference here, you know, around 2. But, you know, you get closer, you see, well, it kind of is a big difference. And again, we're not saying that it's exact. Just because we have 4 terms, it's still not an exact thing. The only place it's exact really is where we constructed it at. But, you know, we may not even have the capabilities to get that close to see the difference. We're super, super close to 0.
Nauseous.
It's not getting bigger.
Yeah, so this doesn't even have the capabilities to do that. But anyways, you see that, you know, that's our series, or that's our finite series rather, approximating e to the x very well, just with 4 terms, right? We'll put that here too. And really the work that we've developed in chapter 10 tells us then, if I want to express this as an infinite series, right, nothing tells us that we have to stop with the 4th derivative. We can keep going on forever and then express e to the x as an infinite series, and then say, all right, well, if e to the x is this infinite series, for what values is that true? For what values does it converge to e to the x? And then that's where all the stuff from chapter 10 comes in. So then, once you have this approximation, you might be asked to use the approximation to approximate e to the 0.1 or e to the whatever. So we can then use this. We can use this fourth degree polynomial which is the fourth order Taylor polynomial. To approximate e to the x for x near, or for inputs near 0. In fact, when you type into your calculator e to the 0.5, this is exactly what your calculator is using. You type in the natural log of 2.36, your calculator is expressing the natural log as a polynomial, and then it's evaluating that polynomial at 2.36. Because it's much easier to do that. It's like the algorithm for evaluating a polynomial is like super straightforward, but the algorithm for even evaluating square roots isn't straightforward. So if we said, all right, what is e to the 0.1? Then we know that e to the 0.1 is approximately the fourth degree polynomial at 0.1, which is 1 plus 0.1 plus 0.1 squared over 2 factorial plus 0.1 cubed over 3 factorial plus 0.1 over 4 factorial. Yeah. So that's equal to 1.1, 0517, 0833. For the approximation, right? The P sub 4 is the approximation. The exact value is 1.1 0517 0918. What is that? 1, 2, 3, 4. It's the error is less than 10 to the -6, just using 4 terms.
How many terms is the calculator use?
I'm not sure.
Oh, okay.
It depends on how many levels of accuracy you say, like float 10 or float 9, whatever. It has to use, and we can talk about the remainder in Taylor's theorem too, the error, but it uses some sort of variation of that, I'm sure. So this is approximate using P sub 4. What if we said now use this polynomial to approximate e of 3? What do you think would happen? Probably be kind of bad. So we'll talk about how to correct for that next class. Do y'all have any questions before we go?